So usually when talking about microservices, you read and hear a lot about success stories from the large industry players like Netflix, Amazon, eBay, just to name a few. And when you look at those success stories, especially from a startup perspective, with far less resources and far less experience in this large scaling world, you might be very tempted to say, well, that looks really great, just let's copy that. But the problem is, what works in one organization might not work for you. And there exists no golden rule that's easily applicable. And so the journey to microservices is different for every organization. And the problem is, or the challenge is, that every organization has to face different circumstances. They are all affecting your transformation journey. So for example, you have your team structure, your skill set, and your team size, and it depends on your transformation velocity. It has a huge impact on how fast you can go with your transformation journey. For example, if you are a small team with little DevOps practices in place, it might be a little slower than if you have already DevOps practices in large organizations in place. And also, one thing that you still have to consider is that you still have to take care of a legacy system. You still have to maintain it, and that's the time, the maintenance effort that you still have to take care of it, is also reducing the time that's available for transforming your monolith into microservices. So, and also your runtime environment of your current system, of your current solution, has an impact on your journey itself. So, can you is it running on premises, or is it running on cloud native? So, can you rely on managed services, or do you have to set up everything from scratch and maintain and run it by yourself? And if your strategy is to introduce new features in a very short period of time, you might struggle with a decision where to implement these new requirements. Shall I add them as a new service, or shall I add them to the current system, to the legacy system, and risking ending up in feeding the monolith instead of shrinking it? So to give you a little background, I am Susanne Kaiser. I used to be the CTO of Just Software. That's a startup here in Hamburg. And at Just Software, we are developing, I still say we, by the way, we are developing the solution Just Social. That's a digital workplace providing collaboration apps for communicating, collaborating in your teams. And so when we started a couple of years ago, we started with a monolith in every aspect. So we had one team working on one collaboration product, implemented as one code base based on one technology stack. So that was quite fine for a while. Everything worked very smooth. We had only little features to implement, but after a while, everything evolved. So our team was growing. We were adding more and more features. Our code base got bigger and bigger. The number of users increased. So this is supposed to be fantastic, but after a while, everything was feeling kind of clunky, very tied together. So from the organizational perspective, it took a long time to get things done. For example, our decisions, our discussions, our meetings took longer than before. And we had not really clearly defined or assigned responsibilities. So it took a while. For example, someone felt responsible when, for example, a bug occurred. Who's taking care of it? So our processes were slowing down and our productivity suffered. And if we look at our product, the more features we added over the time, the more complex its usability became. So the usability and user experience suffered through continuous feature amendments, and instead of solving our users' problems very well, we were increasingly confusing them. And from the software architecture perspective, it's also due to its monolithic structure and monolithic architecture itself. It's pretty complex, or it's quite difficult to add new features without affecting the entire system. So if we want to modify one or add a new feature itself, it's pretty complex to release it, since we have to rebuild and redeploy the entire monolith, even though we just have modified one single line of code. So this resulted then in high-risk deployments, which happened then less frequently. So our new features got released very slowly. So I guess more than 3 years ago, we were focusing on changing our product strategy. And we were focusing on usability and user experience improvements. And we developed the idea to split our one monolithic product itself into separate collaboration apps, and each of them is taking care of a specific use case. Each of them is taking care of handling one problem and handling this problem very well. So we developed the idea to provide apps for sharing documents, for communicating in real time, for managing tasks, for distributing corporate news, and also some knowledge itself. And along with this, or in the meantime itself, we were also splitting our one team into multiple separate teams and assigned to each of them a specific set of collaboration apps, so that we can have different teams. That for each team we have then well-defined responsibilities to enable those teams to work autonomously and independently, to work independently on each collaboration app. So, and as a next logical consequence was that we also reflect autonomy and flexibility also in our software architecture by introducing microservices. And this journey itself was not triggered in the first from the technical perspective in the first place, but was mostly triggered by our organizational and our product changes that we did before. So our motivation to introduce microservices is to enable autonomous teams working at different parts of the software independently at their own pace, at their own speed, with minimal impact across the teams. And we want to enable them to develop and deploy the collaboration apps independently, and also scale them more effectively in production. And the main focus is to release changes quickly to increase the product velocity itself. So we decided, okay, let's try microservices. So the big question that we had, so how to start that one? So, and there's one thing, the first step that we followed was to identify good candidates for microservices. And Lisa was also talking about business domains. And one thing is that you can start with is to follow some specific key concepts. And these key concepts follow to monolith microservices. And the key concepts follow the principles of high cohesion within a service and loose coupling between services. And high cohesion within a service is usually reflected by related behavior that shall stay consistent. And in domain-driven design, related behavior is usually reflected by a bounded context that is a semantic boundary around a domain model where a domain model resides in. And a bounded context describes services that are responsible for well-defined business function. And in our case, our bounded context that we took as a first step was our collaboration apps, to take them as very high-level bounded context describing coarse-grained services as a starting point, which we then can divide in finer-grained services later on. And we started with our document management app, Just Drive, and a very simplistic domain model is Just Drive itself. The documents itself is created by an author, and the author data is stemming from the profile data, and the profile data itself, the data authority over profile data is controlled or owned by a bounded context, which is still residing in the monolith itself. So what we did is that we used this first bounded context that we identified as a good candidate to extract is that we started with coexisting service from scratch. And this coexisting service from scratch was not an exact equivalent. I'll come back to this one later. Instead, we also added new features, we extended the user interface, and we made significant changes to the data structure itself. But anyhow, so we started with this Just Drive collaboration app, and we then had the bounded context of this new service itself is composed of the domain model that is taking care of the business logic, the application service itself that's orchestrating use cases and also manage transactions, and the input and output adapters, the REST API, and also the persistent management itself. And this service itself shall own the document state exclusively. So that's the only service that can read documents but also write documents. That's the only service that can do this. And as I said before, we also had, each document is created by an author, but this author data itself is stemming still from the monolith. So how to handle this data? And there's one approach that we followed that we introduced in event-driven service interaction. So to avoid requesting the author data from the profile service where it's stemming from each time when we're displaying a document, we kept a local copy in our document service itself. And so that we don't have to do request each time the author data when we're displaying the document itself. And to keep this local copy of the author data in our new service in sync with the original data stemming from the monolith, we established an event-driven state transfer itself. So our monolith has to notify our new service whenever a profile has been updated. And so this one, the monolith itself is publishing a profile updated event to a message broker that our new service is subscribing to. So whenever a profile has been updated on the monolith side, it gets an event, the domain service itself gets an event and can update its local copy accordingly. So in hindsight, in general, I would say that a coexisting service from scratch is in general a good decomposition strategy, but especially if you would like to move away from something. For example, if you would like to move away from obsolete business logic, or if you would like to move away from your tech stack. So that's a good decomposition strategy, but as I mentioned before, we weaved in too many steps at once. So as I mentioned, it was not an exact equivalent of the monolith drive service itself, which was residing on the monolith. Instead, we also modified the user interface. We extended it. We added new features in the same process step as well. We made significant changes to the data structure. And what happened is that it took really, really long for the first candidate that we decomposed out of our monolith, and it took so long that we got really frustrated because we could not really gain any experience. We could not gain any early experience. We couldn't gain any early results. So, and that was frustrating because we all had this mind. We want to increase product velocity, and we are really slow now. We are slower than before, and so for us it was not that optimal approach to start with. So what we did then instead with the next one, we were focusing then with the next one with the coarse-grained bounded context of the chat app for communicating in real time, and we followed incremental top-down approach. So it's still a very high-level bounded context itself, and we split it in steps from top to down. So we extracted at first the user interface and provided on the monolith and REST API that the new extracted user interface could connect to. And this allows us to develop and deploy the user interface independently from the monolith and let us iterate over on the user interface rapidly. And then the next step we were going down then from user interface next to the bounded context as to the business logic itself and extracted the business logic from the monolith to the new service itself, which created very significant code changes on the monolith side to extract this one. And at this step, it's we are still accessing the same data. It's still residing in the monolith itself. So, but to become an independent, standalone microservice, it's required that it owns its own state, so its own chat state. And in every chat discussion, chat participants are involved. And as described earlier in the Drive example, chat participants are also stemming from the profile data, which is still held by the monolith itself. And we here also introduced event-driven service interaction that we kept a local copy on the new service that we extracted and subscribed to the profile updated event as soon as the profile has changed and updated it accordingly. So if you have to figure out how to start this and if you have already identified your bounded context at the first step, so good candidates for microservices, and the next step is like how to prioritize it. So I would highly recommend, from looking hindsight, is that so I'd suggest to start with those services that are easy to extract. Because when you have services that are easy to extract, you are getting very fast results. So for example, that you have small services with very few dependencies, for example, that you can extract first. And then you getting very fast results or early results, and can also gain early experience with microservices with them in particular, but also with the extraction process in general itself as well. And you can also focus on those candidates that you have identified as next in your prioritization that are whose extraction gives you the most benefit, because you still have to focus, okay, microservice shall generate a business value for you. And so, for example, you can then focus on services that change very frequently, because after you have extracted it and extracted it into its own independent service, you can then deploy it independently from the monolith itself, so that you can release your changes very quickly without touching the monolith itself. Or you can also focus on those services that are requiring different resource consumption. For example, if you have a service that requires a lot of memory, you could then scale it more effectively on instances with higher amount of memory afterwards, so that you can also generate some scaling benefits after that one. So for example, we had one service that was generating a document preview, and we extracted this document preview service, and after that we could deploy it on instances which had more CPU power and also more disk space as well. So because it was using different resources, or has a different resource consumption than the rest of the monolith itself. And with every service, that's also the next pain point I'm talking about. So with every service that we try to extract, we are confronted with the question how to handle authorization. So to give you a little context, our authorization is very, very fine-grained. We have on the one side the fine-grained authorization down to domain object level. For example, when you can authorize a document based residing in a specific parent folder or a share folder, and the authorization, if you can see it, if a person logs in and can see it or modify this document or upload a new version of the document, depends on the authorization setting of its parent folder. So that's really down to object level. But on the other side, and this was causing a lot of headaches, is the inter-service dependencies. For example, that you could a domain object its authorization can depend on authorization settings of a parent domain object which resides in a different service. For example, if you would like to upload a document to attach a document to a wiki page, for example, to a content page, if you have the rights, depends on the authorization settings of the wiki page which resides in a different service than the document itself. So, and these complex requirements caused us a lot of headaches, which resulted in that we were not solving the distributed authorization handling from early on. And this then created some really counterproductive consequences. So on the one side is, since the distributed authorization handling was not in place from early on, one consequence was, okay, then I have a new service, I have a new candidate for a service, I need authorization, where do I put it? Let's put it to the place where authorization handling is already provided, and there was in the monolith. So we added the service to the monolith again and feeded the monolith instead of shrinking it. That was one counterproductive consequence. And on the other side was that we were, since distributed authorization handling or centralized approach was authorization handling was not provided yet, we were re-implementing it on service level. So we were re-implementing a cross-cutting concern per service. So and the thing is, what the first from the first assumption was that you could think that that authorization belongs to the domain model and belongs into that service. But the problem is we missed the fact that we have the inter-service dependencies. So we were copying data back and forth all the time. So in the long run, we merged it together to one centralized authorization service and provided that one. But when you provide a centralized authorization service, you are facing another challenge. Oh, I'm sorry, I just want to summarize our headaches. So the thing is, the learning that we gained from that one is handle cross-cutting concern early on, then you don't run into these counterproductive consequences. But if you provide a centralized service, then you can run into another challenge, and that is the problem, or that you might provide a distributed monolith. For example, if you would like to change one side of your system and you have to change another side of your one service, and you will have to change another service simultaneously, you have to deploy them all together, then it's a strong indicator that you have introduced a distributed monolith. And that's for example, when we let's think of if we introduce a totally new collaboration app. And if we would like to implement authorization handling in this new collaboration app, and we have to at the same time have to adjust the authorization service itself in the same time, otherwise authorization wouldn't work, then we have the downside, then you have the disadvantages of both worlds. They're still coupled because you have to adjust both of them and redeploy them at the same time. And they are now communicating over a slow and unreliable network, and the complexity increases. So to avoid this, we introduced a common contract, and that the authorization service itself owns, and each downstream service itself translates to. So for example, if we have a collaboration app that would like to know if would like to trigger some authorization related actions, it translated to these common contract that the authorization service understands, and the authorization service does not need to be touched. That means if we introduce a new service, the authorization service is untouched from that one, and can then and you can plug in new services without redeploying the authorization service itself. But one prerequisite is that this common contract that the authorization service owns is stable. Otherwise, if you change it a lot of times, then you shift the problem to the other side. Then you have to adjust all the downstream services itself. So, and when you so after you have also taken care of cross-cutting concerns as well, you still have to figure out how our services shall interact with each other. So you have identified the candidates, you have now decomposed them, you have taken care of your cross-cutting concerns, and now also with every service that you introduce, the question comes along like, how shall my services, my extracted service now communicate with each other? And there are some different service interaction types. You have the request-driven interaction, where one service knows or calls the other service directly over its API, for example, a REST API, and which gives the calling service the opportunity to control the request flow if there is synchronous processing in place, but with the downside that you are coupling those services together at runtime. And in the event-driven service interaction approach, you have the communication itself. It's not the services themselves are not calling each other directly. Instead, they are communicating over a message broker, over events. So, for example, on the one side, we have a service that publishes event to a message broker, and it doesn't care if the other service on the other side is up or not. It just publishes to the message broker. That's the only interaction that it has. And on the other side, the service that subscribe to these events, they can consume it at their own pace independently. And so that flips the flow control to the receiving end and increases the decoupling between the services, and also increases autonomy and also pluggability. And in a hybrid model, these patterns are combined. You have a request and a request response interaction, but also an event-driven interaction that I can explain a little later. So because then in the next question, so if you now have to figure out like which service interaction you should use, you also are confronted with the question how to manage shared data. For example, in the document example, we still have the author data. We have documents data, but also author data which stems from another service. So how to share this data? And so in the hybrid model that in this combined patterns, you have the services are communicating via events over a message broker, but only for notification purposes. So in case additional data is requested from another context, it does a direct a remote query, cross-context query directly to its source. So you may prefer this kind of service interaction because of its simplicity and its flexibility over maintaining a data set locally, which also could grow over the time. And but the problem is that you still have a remote query directly to the source, which increase the coupling between those services. And to avoid a remote query, you can internalize it by a local copy, by keeping a local copy on your server side. And as described in the previous Drive example, to avoid requesting the author relevant data from the profile service each time we're displaying a document, we kept the local copy. And in this case, when you keep a local copy, you have to also consider or to take care of it that it's kept in sync. You have to maintain that it's in sync with the original data. But in this case, you're using events not only for notification purposes, but for data duplication purposes. So the event now have a larger payload. It's not only saying, okay, this profile one has been updated. Now it says profile one has been updated with this data, for example, and that you can retrieve this data from the event itself and update your local copy accordingly to the data that the events itself it's transporting. The downside of this one is, so it increased the decoupling between the services as a benefit, and also it increased because we have no remote queries anymore, and it also increased the autonomy because the service can do whatever it likes with its local copy, and it makes the joins also more efficiently because the joins are now local, and you don't have to go over the network. But the downside of this is that you have a duplicate copy. First you are duplicating it, and the next thing is you have to take care of it, that you have to keep it in sync with the original data. So that's something that's an overhead that comes into this style. And another aspect that you also have to consider when you decide on service interactions, also the source of truth. So in traditional event-driven systems, you usually listen to events, saving your actions into a database, and you are emitting new events. And for your service itself, your database is your source of truth. But for all downstream services, the events are your source of truth. And this results also, there are two challenges. So the one challenge is that you have dual rights. You're saving a state into your internal database, and you're emitting a new event. So, and you somehow have to figure out how to maintain the consistency. And another challenge that happens in this way is that the data model of the database and the data model of the events can diverge very easily. And as an alternative, you can emerge those by retaining the events long term, that you then make the events as first-class citizens, as a primary data source itself. And in this context, Apache Kafka comes in place, which is well suited for retaining events long term and used as an event store. So who of you have heard of Apache Kafka before? Quite a while, so, quite a few. And also, who is using it in production? Okay, a little less. Okay, so Apache Kafka itself, it's a distributed fault-tolerant, scalable commit log service, which was originally created by LinkedIn, and it's open source. And for example, Netflix is using Apache Kafka very heavily. They're transferring over 1 trillion messages per day. So it's really, really scalable, really, really fault tolerant, and Netflix is also using this very heavily. And so Apache Kafka itself provides different capabilities. So it can be used on the one side as a messaging system, but also as a storage system for retaining events, and also as a streaming platform. And so we have used Apache Kafka from early on, but mostly in the very beginning first for notification purposes, then for event-driven state transfer. And recently we have introduced Kafka Streams as well. And so in Kafka Streams, or streams in general, it's an unbounded ordered sequence of structured data records, and each data record is just a simple key value pair. And the streams are continuously updating. And so when you start a stream in your service, what happens is that a Kafka topic is automatically loaded into your streams, which can be processed by you in the scope of your own service. And a Kafka topic is that's simply a logical category where you can publish messages to or consume messages from. For example, we had a document topic where the document change events were residing in. We also have a profile topic and so on. And each stream itself, it's buffered by an embedded lightweight database. And you can also, that's called a state store, and you can also generate your own state store. I come to this in the next slide. And the stream, it's running in the same process of the microservice. You don't have to, it's running on in your own code base, and you don't have to contact the broker itself. It's just so the streams themselves, they make data available wherever it's needed. So it's a very, very powerful tool, because then it increases also the performance. You don't have to do a remote call, and also increase autonomy. And Kafka Streams, they provide a stream API which lets you join, filter, group, and aggregate your streams using domain-specific language, a DSL. And every every message in the streams can be processed by function-like operators like transform, peek, map, and so on. And on the other side is that whenever you would like to implement stream processing, you have the requirement to implement a stream, but also a database for enrichment. And and here comes also in Kafka streams, they provide a core abstraction over streams and tables for database enrichment. And the streams and the tables, they are really closely related. So, for example, a stream can be considered as a change log of state changes, where each data record itself in the streams captures the state change of the table. And on the other side, a table can be considered also as a snapshot of the latest value at a time for each key in the streams. So, and this lets us to very powerful switch from stream to table very easily, which helps us processing then the messages in the stream. And I come to this one here right now. So, for example, when we now would like, if we go back now to the document service, where we kept a local copy of the author relevant data to avoid requesting the profile service each time we're displaying a document. What you can now do is a different approach, because to reduce the overhead of keeping a local copy, we can now create a stream, because we have retained the events that carries the document and the profile data in the stream itself. And what we can now do is we can create a stream from the document topic and create a table from the profile topic to enrich the document data with the author relevant with the author data. And now we can join the stream and the table together and store its result in its own state store, which can be accessed from externally from a REST API and can be used as a materialized view. So whenever, for example, now your document got updated or a profile got updated, what happens is that your states or your materialized view that you can display your document with your author data, that it's updated automatically without any interference from your side. So you only have to create a stream, create a table, join them both together, and that's it. And you don't have to keep a local copy somewhere. You don't have to do a remote request to another service. Everything is provided by Kafka Streams itself. So compared to the other event-driven service interactions, streams themselves, they eliminate the local copy, which reduces the overhead of keeping a duplicate copy and also maintaining its data. And also due to the stream functionality, it pushes the data to where it's needed. It pushes into your service itself. So it's running there in your service, not at a broker itself. And this also increased pluggability. For example, if you already have your event streams, you can plug in a new service, and you don't need, depending on what amount of data you have already in your stream, that you don't have to have your own data store anymore. So it's you can just rely on the services on the streams themselves, and this increases the pluggability and also autonomy and flexibility and performance, and lower also the barrier to entry for new services. And to summarize what we have learned so far, or what I was talking about, is that from our perspective, what we would recommend if we would start the journey again is that we would start small with small services that are easy to extract, to gain early results with microservices, and thus gain also early experience with microservices and its extraction process. And also focus on that one, what's one manageable step at a time. So if you're a small team, then the steps should be related to a team size itself. And also handle your cross-cutting concerns early, I would recommend. And if you provide centralized service, watch out for introducing a distributed monolith. Try to avoid introducing a distributed monolith by providing a common stable contract. And to design your system to be easy to evolve, consider event-driven service interaction, and also between your services, but also you could also consider event streams to increase the pluggability between those services. And to come back what I've mentioned in the beginning, be aware of your affecting circumstances and watch out for what's holding you back. Where are you struggling or pain points for all the circumstances that are affecting your transformation journey. And try to adjust it, and if you can't adjust it, at least create some awareness. So you can't implement a lot of new features in the same amount of time as you did before if you are in parallel also start with your microservices journey, because this is, especially in the beginning, if you have little experience as we had, it's really time consuming, and it's an investment. It's not in the first, it's not cutting costs, but it's more focusing on increasing your product velocity and your time to market. And also consider each journey is different. So our obstacles that we had, you probably will never have. And that's totally fine. And because everyone is facing different circumstances. Thanks a lot.